All right, good morning, guys. Let's go ahead and get started. So to begin, if the perimeter of a rhombus ABCD is 208 meters, and the measure of angle ABO, this angle right up top here, is 30 degrees, we want to find the measure of segment OD. So, to begin, first off, what properties of a rhombus do we know? Well, in a rhombus, we know that all four sides are congruent. So therefore, if the perimeter, the whole thing, is 208 meters, and all four sides are congruent, then I can take 208 meters and divide it by four congruent sides. That will give us 52 units per side. So every single side here is 52. Now, another property of a rhombus that we know is that the diagonals are perpendicular to one another. So they intersect each other at 90 degrees. So therefore, I know that this angle is going to be 90. Now, we also know angle ABO is 30 degrees, as we stated earlier, which makes this a 30, 60, 90 right triangle, which is a special right triangle. So this obviously allows us to use some properties here. So I'm going to go ahead and draw up what we know. So since this is a 30, 60, 90 right triangle, we have our 30, 60, 90 right triangle right here, where the side opposite 30 degrees is x, the side opposite 60 degrees is x radical 3, and the side opposite 90 degrees is 2x. Over on our actual triangle, the only side that we are actually given is the side opposite 90 degrees, which is 52 units. So that means the side that's opposite 90 degrees is 2x, but the side opposite 90 degrees is also 52. So I can set up an equation as 2x equals 52. Solving for x here, we get x equals 26. So the side opposite 30 degrees is x. So that means in our original triangle, the side opposite 30 degrees is 26. Similarly, if the side opposite 60 degrees is x radical 3, and x is equal to 26, then the side opposite 60 degrees is 26 radical 3. So that means from point B to point O is 26 radical 3 in length. Now another property that we have of rhombi is that the diagonals bisect each other. That's a property of a parallelogram. So therefore, BO is congruent to OD. Now, if we're trying to find the measure of OD, and it's the same as BO, well, BO is 26 rad 3, so OD must also be the same unit. OD will also be equal to 26 radical 3. All right, so today we're going to be doing 5.5 properties of quadrilateral notes. Our learning target is I can prove properties of parallelograms, and I can solve problems using properties of parallelograms. So let's go ahead and begin. So first off, this slide here just has all the properties of parallelograms, of kites, and of different types of trapezoids. So this is something that we covered in our 5.1 notes. You guys don't need to copy it over again. Just know that it is here in case you guys need to fill out some of these properties, in case you don't have them all. So, ways to prove a quadrilateral is a parallelogram. Today we're going to be given quadrilaterals and we need to prove that they are parallelograms using these 5 ways. So the first way that we can do this is if both pairs of opposite sides are parallel. So if opposite sides are parallel, if opposite sides are parallel, that's enough to say that the quadrilateral is a parallelogram. If opposite sides are congruent, that is also enough to say that we have a parallelogram. If one pair of opposite sides is both parallel and congruent, this one's really important because it will show up down the road. So if one pair is both parallel and congruent, then we have a parallelogram. If the diagonals bisect each other, that's enough to say that we have a parallelogram. And then our final way is if all consecutive angles are supplementary, then the quadrilateral is a parallelogram. And it's very important that it's all of them. It's not just one or two of the angles, one or two pairs, it's all of the pairs. So any consecutive angle must be supplementary to the next. That is when it's a parallelogram. If it's not all of them, but only two pairs, then chances are it's going to be a trapezoid. But if it's all of them, then it's going to be a parallelogram. So let's go ahead and try out our first proof. Given ACDF is a parallelogram and angle AFB is congruent to angle ECD, we want to prove that this figure in the center here, FBCE, is also a parallelogram. So to begin on this, we're going to go ahead and start by writing out our given information. Our given information is that ACDF is a parallelogram and angle AFB is congruent to angle ECD. We draw that in our picture as well before we begin. Now, since we're given a parallelogram, we want to use one of the properties of a parallelogram to get started. And out of all the properties of a parallelogram, the one that we can use to further this proof is that opposite sides are congruent. So I can say that AF is congruent to CD. And the reason that we can say that is because if this is a parallelogram, which we have in statement number 1, then opposite sides will be congruent. Now, what I'm trying to do here, I have an angle and a side already within this triangle AFB. So what I can do is, if I can prove that these two triangles are congruent, then I can do some more work on our interior quadrilateral. So, next up, I'm going to use another property of a parallelogram. That property being angle A being congruent to angle D. So what property of a parallelogram would allow us to say that angle A is congruent to angle D? Well, that'd be that opposite angles of a parallelogram are congruent. Well, now looking at these two triangles, we should have enough information to prove that these two triangles are congruent. If we start anywhere on our triangle that doesn't have congruency marks, and I just start moving around my triangle, the first congruency mark I see is for an angle, followed by a side, followed by an angle. So therefore, triangle AFB is congruent to triangle DCE by angle, side, angle. Now, since these two triangles are congruent, if I look at this, I'm going to go ahead and use some of that information to prove some information on our quadrilateral in the center. So if I look at FB, it's second and third. CE, also second and third. So FB and CE are corresponding because they're written in the same parts. They're also corresponding of congruent triangles. And we know corresponding parts of congruent triangles are congruent. So we can say that FB is congruent to EC by CPCTC. Corresponding parts of congruent triangles are congruent. Next up, AB is congruent to ED. The reason I can say this, well, A and B are first and third. D and E are first and third. So they're corresponding parts of congruent triangles. And we know corresponding parts of congruent triangles are congruent. So reason number 7 is the same exact thing. Now, this already gave us opposite sides. One pair of opposite sides is congruent in this quadrilateral. We're looking for the opposite pair as well, FE and BC. So, to get there, I'm going to go ahead and go back to statement number 1. I'm going to focus in on our big parallelogram up here. So I'm going to use one of our properties once again, and I'm going to say that segment FD is congruent to segment AC. The reason I can say that these entire segments are congruent is the same exact reason as 3, that opposite sides are congruent. Opposite sides of a parallelogram are congruent. So I now have this entire segment, and I also have these smaller segments, ED and AB. So what were to happen if I took segment ED away from segment FD? Well, I'd just be left with segment FE. Similarly, on our other side length, if I took AB away from AC, I'd just be left with BC. So FE is congruent to BC, and the reason I can say that FE is congruent to BC is by the subtraction property. So I'm just subtracting a segment from a longer segment. Well, now if we look at this quadrilateral in the center here, I have two pairs of opposite sides that are congruent. And if we think back to those 5 reasonings that we just talked about, that's one of our reasonings. So I can now say that FBCE is a parallelogram, and the reason that we can say that is because if opposite sides are congruent, that implies that we have a parallelogram. And this proof is now complete. All right, next up. Given Triangle CAR is isosceles with base CR. AC is congruent to BK, and angle C is congruent to angle K. We want to prove that BARK is a parallelogram. So, again, we start off with our given information. And before we actually write this and draw it in, think about what type of shape this is here. Think about what type of shape ABKC is. Well, if we look at it, with all this given information, this is actually an isosceles trapezoid. We have two legs that are congruent, and we have congruent base angles. So this is an isosceles trapezoid. We want to prove that we have a parallelogram within. So, to get started on this, let's go ahead and first work on our triangle with the side lengths. Since this is an isosceles triangle, I can say that CA is congruent to AR. And the reason that we can say that is because it's an isosceles triangle. And we know that two legs of an isosceles triangle are congruent. From here, I'm going to go ahead and focus on statement number 2 and statement number 4. I can see that AC is congruent to BK. And in statement number 4, I can see that AC is congruent to AR. So what if I skip past AC completely? Could I say that BK is congruent to AR? Well, absolutely, I can skip past AC. Which property would allow me to say that BK is congruent to AR? Well, that'd be the transitive property. Anytime that I'm skipping past a segment, it's the transitive property. So I now have that AR and BK are congruent. From here, we're going to focus in on the angles. So, looking back at our isosceles triangle, angle C and angle CRA are congruent to each other. The reason that we can say that these two angles are congruent is because it's an isosceles triangle. We know if legs are congruent, then base angles are congruent. Well, now let's focus in on statement number 3 and statement number 6. Angle C is congruent to angle K, and angle C is also congruent to angle CRA. So what if I skipped angle C? Is that allowed? Absolutely. I can say angle K is congruent to angle CRA by the exact same reasoning as number 5. I'm skipping past angle C. It's by the transitive property. So now I have these two angles that are congruent, which means that CK is a transversal line. AR and BK may be parallel based upon the angle relationship that's happening between angle CRA and angle K. Now, since angle CRA and angle K are congruent, that gives us some good information. What is their angle relationship, though? Well, their angle relationship, they're on the same side of our transversal. One is inside the perceived parallel lines. One is outside the perceived parallel lines. And they have a different vertex. Therefore, these are corresponding angles. And we know corresponding angles are meant to be congruent if we have parallel lines. Since these are congruent angles, I can say that segment AR is parallel to segment BK. Because they are corresponding angles and they're congruent. And if corresponding angles are congruent, that implies parallel lines. Lastly, since we have one pair of opposite sides that's both congruent and parallel, we can say that BARK is a parallelogram. Because again, this is one of the special ones that I mentioned. If one pair of sides is both congruent and parallel, that implies that we have a parallelogram. All right, next up, our final proof of the day. Given angle XRV is congruent to angle RST, and angle RSV is congruent to angle TVS. We want to prove that this figure here, RSTV, is a parallelogram. So again, we start off with our givens, and this time we're going to focus a lot on angle relationships. So I'm going to start with our black angles, angle XRV and angle RST. So these two black angles here. Now, as we can see, SX is a transversal line. It's touching both of these angles. It's going along both of these angles. And the lines that we want to show are parallel are TS and VR. So we're going to be looking for the angle relationship here. Now, what's the angle relationship between these two black angles? Well, one is interior, one is exterior. They're on the same side of our transversal line, which means that they're corresponding angles. We know if corresponding angles are congruent, just like in our last proof, that we have parallel lines. So therefore, TS is congruent to VR. It's not congruent, parallel, sorry. TS is parallel to VR. And the reason that we can say that is because if corresponding angles are congruent, then that implies parallel lines. Next, let's focus on our blue angles. So this time SV is our transversal, and it's intersecting our two parallel lines, are the two lines that we want to show are parallel, TV and SR. So, what is their angle relationship? Well, they're on alternate sides of the transversal line, opposite sides. They're inside the perceived parallel line, so they're alternate interior angles, which are supposed to be congruent. And from statement number 2, we see that they're congruent. So therefore, I can say that TV is parallel to SR. And the reason that we can say that is because if alternate interior angles are congruent, which we have in statement number 2, that implies parallel lines. Lastly, if we look at this figure, RSTV, we now have enough to say that it's a parallelogram. The reason why is because both pairs of opposite sides are parallel. That's the definition of a parallelogram. So this proof is now complete. All right, let's go ahead and move on to some explanations of showing how to do things, then we'll go through some always true, sometimes true, or never true questions. So, given quadrilateral quad, we want to show quad is a parallelogram. So get started here. They give us angles. They give us all 4 angles here, and we want to show that this is a parallelogram. So one of the properties of a parallelogram that we can use is that opposite angles are congruent. So therefore I can say 3x times x squared minus 5x is equal to 3x cubed minus 5x squared. And x squared raised to the 5th power is equal to x to the 10th power. So we can go ahead and write those out right away. And we're just going to go ahead and check and see if they're equal. That's how we can show this. So I distribute the 3x through the parentheses. 3x times x squared will give me 3x cubed. 3x times negative 5x will give me negative 15x squared. So therefore, they are equal to each other, and it checks out. As for our second one, we have x squared raised to the 5th power is equal to x to the 10th. That means that exponents of exponents, we multiply these. So this would give us x to the 2nd times 5th power, which is equal to x to the 10th power. So this one also checks out. Just as a recap, properties of exponents, if I'm raising an exponent to another power, I multiply. If I have x to the 5th times x to the 4th, if I'm just multiplying and they have the same base, the same number here, in this case it's x, now I'm just going to go ahead and add those exponents. So just a little bit of exponent refresher. Don't forget about exponent properties. Those will be important for you down the road. But again, that's just a little bit of a refresher there. If you're raising an exponent to another exponent, always multiply. All right, moving on to always, sometimes, or never true questions. First off, all squares are rectangles. So to look at this one, we go ahead and we draw out our entire family for parallelograms. So as we can see, we have squares right here. We have rectangles right on the outside. So it looks like rectangles encompasses all the squares as well. So therefore, this will always be true. A square will always be a rectangle. Next, the diagonals of a parallelogram bisect each other. Well, if it's a parallelogram, that will always be true. Here I draw a rectangle. And when we have these diagonals, these blue diagonals, they will always bisect each other. They'll always cut each other in half. So that is always going to be true, no matter what, because that's a property of a parallelogram. Next up, all rectangles are squares. So again, I'm going to draw my family. Here's the entire parallelogram family. And as we can see, not all rectangles are squares, but some of them are. So therefore, a rectangle that is a square has all sides congruent. So this is sometimes true. It happens, but not very often. It only happens when we have a square occurring, or when all four sides are congruent. Next, the diagonals of a rhombus are perpendicular. So if we draw a rhombus out, there's our diagonals, they're all perpendicular. This is always going to be true because this is a property of a rhombus. It's not going to change, it will always remain the same. Next up, opposite angles of a parallelogram are supplementary. So here's a couple parallelograms. And as we can see, the top one, we have opposite angles that are congruent here. We're wondering for supplementary. In our second one, if they're all 90 degrees, well, 90 plus 90 is 180, that's supplementary angles. So this is sometimes true only if it's a rectangle or a square, only if we have all right angles here. That's the only time that opposite angles will be supplementary within a parallelogram. Next, all angles in a rhombus are congruent. Well, that is only true as well if we have a square, because then we'd have 90-degree angles all the way across, which would make all angles congruent. Next up, consecutive sides of a rectangle are congruent. Consecutive sides of a rectangle are congruent. Well, if we draw two rectangles, again, I can see in this rectangle over here, all consecutive sides are congruent. So this is sometimes true. It only works if it's a square. Diagonals of a rectangle bisect its angles. So if I draw two rectangles, here's a square rectangle and then a normal rectangle. And I have my diagonals. We're looking at the angles here. So this is sometimes true. It only works once again if it's a square, because the square will cut them all into 45-degree angles. Diagonals will not bisect the angles within a rectangle. Again, diagonals will not bisect the angles within a rectangle, unless it's a square. All right. Opposite sides of a trapezoid are congruent. So if I have a trapezoid here, and here's my second trapezoid, the only time that opposite sides of a trapezoid are congruent, and it's only one pair of sides that can be congruent here, is when we have an isosceles trapezoid. That's the only time. So therefore, it's only going to be sometimes true. It's not always going to be true. All rectangles are parallelograms. Well, again, I can draw my parallelogram family. And we can see that rectangles lie within the parallelogram circle. So therefore, this is always true. Rectangles are part of that family. Our final always, sometimes, or never true question, the diagonals of a square form four right triangles. So if I draw my diagonals through my square, we can break this up. And since we know all the properties of squares, we know that the angles will be bisected because it's a rhombus. We know that the diagonals are congruent because it's a rectangle, that they're perpendicular bisectors because it's a rhombus as well. So we can see that we have four congruent right triangles. They're 45, 45, 90 right triangles. So they're isosceles right triangles. And further, we know that all the sides will be congruent, all the diagonals will be congruent, and all the diagonals to the intersection point will also be congruent to each other. So lots of congruency here. So this is always true. It'll always form four congruent right isosceles triangles. All right. Lastly, for today, we're just going to go ahead and draw these figures up and make sure that we're drawing all these properties, because the properties are the important part. So to start off, we're going to focus on unique properties, starting with the parallelogram. Opposite sides are parallel by definition, so we can draw opposite sides being parallel. Again, I just named my parallelogram PARL for parallel. Opposite angles will be congruent, so angle A is congruent to angle L, angle P is congruent to angle R. Opposite sides are congruent, so PL is congruent to AR and PA is congruent to RL. And lastly, diagonals bisect each other, so AL bisects PR and PR bisects AL. Cutting each other in half. Notice how they're not exactly going to be congruent to each other with these diagonals. The bisections aren't going to be congruent. Not unless it's specifically a square or a rectangle. Then lastly, any pair of consecutive angles are supplementary. So I can go for any two consecutive angles and they'll always be supplementary. So angle A is supplementary to angle R is supplementary to angle L with P P with A. All right, moving on to a rectangle, RECT. So again, we're only drawing the unique ones, so you don't need to draw the properties of a parallelogram, but it's important that you know that all properties work for this. We also know that we have 4 right angles because this is a rectangle, so all angles are right angles. R, E, C, and T are all equal to 90. And then the diagonals, the entire things are congruent. So RC is congruent to ET. Again, I'm drawing my congruency marks on the outside. That way we know that the entire piece is congruent. If I were to draw tick marks on the inside, you may be thinking, oh, this segment is congruent to this segment, rather than the entire thing. So that's why I draw it on the outside there. Next up, I'm going to go ahead and skip down a couple to a kite. So for a kite, we have 2 disjoint pairs of consecutive sides that are congruent. So IK is congruent to KE, ET is congruent to TI. Further, if we had all of these, IT being congruent to TI, IK being congruent to TI, which would be congruent to TE, which would be congruent to EK, if all of them are congruent, the kite can sometimes be a rhombus if all disjoint pairs of consecutive sides are congruent. So, as for our properties, the diagonals are perpendicular. So KT is perpendicular to IE. One diagonal is the perpendicular bisector of the other. So TK is bisecting IE and is perpendicular to it. And again, use your reasoning skills. Obviously, it looks like IE is being cut in half. TK obviously isn't. T to the intersection is much longer than K to the intersection. Now, the diagonal that is doing the bisecting, TK, its angles are being cut in half. So therefore, TK is an angle bisector as well. So that means that ITK is congruent to ETK, and EKT is congruent to IKT. Then lastly, one pair of opposite angles are congruent. The diagonal that is being bisected, it has its angles that are congruent. So angle I is congruent to angle E. Make sure that you know the properties of kites. Those will probably be the most difficult shapes to work with. However, you should still be able to use them. All right, next up, we have a rhombus. Again, we have all the properties of a parallelogram, so you guys don't need to draw those. We're only looking for unique properties right now. We have all sides are congruent. So RM is congruent to MO, which is congruent to OH, which is congruent to HR. So all 4 sides. We know diagonals bisect the angles. So each angle is being cut in half. So angle MRO is congruent to angle HRO. RHM is congruent to OHM. HOR is congruent to MOR. And OMH is congruent to RMH. So lots of different angles that are being bisected. Further, diagonals are perpendicular bisectors of one another, so they're not only cutting each other in half, but they're also intersecting at 90 degrees. Then lastly, the diagonals divide the rhombus into 4 congruent right triangles. So all these are right triangles, and they're all congruent. As we can see, side, angle, side, side, angle, side, so on and so forth. These are 4 congruent triangles here. The last parallelogram that we'll talk about is a square. Now, it doesn't have unique properties, so we're just going to draw the definitions of each of these properties here. So first off, the properties of parallelograms, it has all of those, so opposite sides being parallel is what we'll draw. It's the definition of a parallelogram. It also has all properties of a rectangle. Now, the definition of a rectangle is 4 right angles. Has all the properties of a rhombus. Well, properties of a rhombus is that we have all 4 sides being congruent. And then, of course, as we saw in that always, sometimes, or never true question, the diagonals form 4 right isosceles triangles. So we have 4 right triangles here. And again, they're all 45, 45, 90 triangles. Lastly, for drawing our shapes, we have isosceles trapezoids. So again, in our isosceles trapezoids, our legs are congruent. So TP is congruent to RA. The bases are parallel. TR is parallel to PA. The lower base angles are congruent, so angle P is congruent to angle A, as well as the upper base angles being congruent to each other, angle T being congruent to angle R. And then similar to a rectangle, the diagonals are congruent to each other. So TA is congruent to RP. Lastly, any lower base angle is supplementary to any upper base angle. It doesn't matter. A lower base angle and an upper base angle will always be supplementary to each other. So angle T plus angle P is equal to 180. P and A are supplementary. A and R are supplementary. P and A are not supplementary. I misspoke. P and A are congruent. A and R are supplementary. P and R are supplementary. P and T are supplementary. A and T are supplementary. So those are our pairs of supplementary angles. To finish up today, we just got some final questions. So first off, what is the perimeter of a rhombus with one side length being 12.5 units? Well, if it's a rhombus, we know all side lengths will be 12.5 units. So it'd be 4 congruent sides by 12 multiplied by 12.5, which give us 50 units total. Which quadrilaterals have congruent diagonals? So again, we're looking at quadrilaterals as a whole. Well, we have rectangles, we have rectangles, squares, and isosceles trapezoids. Those are the 3 quadrilaterals that have congruent diagonals. And again, diagonals go through the shape. I'm talking about the entire thing being congruent to the entire thing. Which parallelograms have perpendicular diagonals? Well, there's only 2 of them. We have rhombi and we have squares. They both have perpendicular diagonals. Which parallelograms have diagonals that bisect the angles? So bisecting angles. Well, again, there's only 2 of those. Again, rhombi and squares. They will have diagonals that bisect the angles. So these angles are being cut in half, not the side lengths. Not the diagonals themselves. Well, diagonals are being cut in half, but they're not bisecting each other necessarily. Meaning that they're not going to be congruent to each other unless it's the square, because a square is a rectangle. But in a rhombi, this diagonal will not be congruent to this diagonal. Lastly, which parallelograms have diagonals bisect each other at their midpoints? Well, that's all parallelograms. All diagonals will bisect each other within a parallelogram. So therefore, they're intersecting each other at the midpoints, because if they're bisecting each other, they're cutting each other in half. Where do they cut each other in half? In the middle, so at the midpoints. So therefore, diagonals will bisect each other at their midpoints for every single parallelogram. All right, guys, thank you so much for watching today. If you guys have any questions, please